Up until this point, we've been practicing graphing sinusoidal functions. So if we're given an equation, can we graph? Or if we're given a situation, can we graph? Or if we're given special features, can we graph it? So now we're going to work backwards. What if we're given the real world problem and we're to come up with the equation? Or we're given the graph and we have to come up with the equation or specified features. So by the end of this lesson, we should be able to write equations if we're described a problem, given a graph, or given features like the max and the min and the equation of the axis. So we're going to try our first example where we're given a graph and we're asked to come up with an equation. So it says a nail is located on the circumference of a water wheel and is moving as the current pushes it on the wheel. So we can imagine that the nail is going up and down and up and down and up and down. The height of the nail in terms of time can be modeled by the graph shown. Determine an equation of a sine function and a cosine function that models the graph below. So here is our clue. This is all we know about the height of the nail. We can see it reaches a maximum height of 3 and a minimum height of -1. That -1 makes sense because it's a water wheel. So this must be -1 centimeters under the water, or 1 centimeter under the water. So we know that the general form of an equation or sinusoidal function looks like this. This could be changed with cos, but we have an a value, a k value, a d value, and a c value. And if we find those 4 values, then we'll find the equation of this curve. So let's start with a. We know that a is just the amplitude, and we can absolutely calculate the amplitude. So let's calculate the amplitude right here. We can remember that the equation for the amplitude, it's not the average, it's the distance from the middle to the top. So we're going to take the max minus the min divided by 2. And we can see that the maximum value here is 3 and the minimum is -1. So we'll have 3 minus -1 all over 2, which is equal to 4 over 2, which is equal to 2. And this logically makes sense because we can see the middle is going to be 1, and the distance from 1 to 3 is 2, and the distance from 1 to -1 is 2. So we have our first letter done. Let's work on our next one. So if we look over to k, we know that k is related to the period. And using this relationship, we can solve for k. So if we have the period, then we can find k. So taking a look, if I see that the sinusoidal function begins here, then that would mean that it would end here and the length would be 10. So similarly, if I saw that the function started here and it went up and down, and that's one cycle, the period would still be 10. So if the period is 10, then we can add into our little equation that 360 divided by k has to equal 10. And if we multiply by k, and then if we divide by 10, we're going to be left with k is equal to 360 over 10, which is going to work out to 36. So now we have our second letter. So those two are pretty easy to find. The last one, we're going to skip our horizontal shift for a second, and go to our vertical shift. So to measure the vertical shift, we already talked about that the middle of the graph looks like it's going to be 1. Because if we were to take this max plus the min divided by 2, we're going to get 1. Well, the middle of the graph used to be at 0. And clearly if the middle is now 1, it got shifted up 1. Which means that the equation of the axis of symmetry can be our measure for how much a graph has been shifted up or down. Therefore, we can find C by just finding the equation of the axis of the curve. And we know the equation of the axis is just the middle of the graph, so it's the average of the max plus the min divided by 2. And our max is 3 plus our min is -1 divided by 2, and that's going to be 2 over 2, which is 1. And we had already anticipated that the middle was 1. So that must be our vertical shift. Our last step is to find our horizontal shift D. And the reason why I left it to the end is because that depends whether we see a sine graph or a cos graph. So if we see a cos graph, we know that cos looks like the bowl. So you might see this graph right here, in which case it has not been moved over at all. If you see a sine graph, you see it starting up here, coming down, and coming back up here. Remember, sine does not start at the x-axis. It starts in the middle of the graph, comes up, comes down, and comes back again. So let's break down what the d-value would be for a sine curve and a cos curve. So if you see a cos curve, you're probably seeing this little guy right here. In which case, this guy has not been shifted over at all. It's supposed to, the top of the curve is supposed to be when x is equal to 0, and it is. So if you see this curve, then you would choose that the horizontal shift is 0. Alternatively, you might see the cos curve here. And if you see the cos curve here, then your horizontal shift would be 10 over because it's starting at 10 rather than 0, and that's completely fine. There's actually an infinite number of answers to this problem. We could come up with an infinite number of equations to represent this graph here. So we also might see the cos curve here, in which case you say it would be shifted to the right 20. We're asked to come up with an equation for a cosine function and a sine function. So we have everything that we need for a cosine function, but for a sine function, we don't know what the horizontal shift is. So first we got to be able to see where the sine function is. And the sine function is going to come up, come down, and come back again, just sort of looking like that S. So we have to figure out where does it start. Well, the minimum point in terms of the x value starts at 5, and the maximum ends at 10, which means that in the middle, this point here must be in between 5 and 10, and the number in between 5 and 10 is 7.5. So this means that this must have been shifted over. If we think that the sine graph starts here, it must have been shifted over to the right 7.5. So that's what our d value can be. Alternatively, you might see a sine curve this way, where it's been shifted to the right 2.5, but then it's been reflected in the x-axis, and that's absolutely fine. So your a value would be negative, and it would be shifted to the right 2.5. Another option you might see is you might extend this line like this and say that the sine curve starts here and ends here, which case you would say that it shifted left 2.5. So I think we've gone through about 4 different options that you could put for sine, and there's an infinite number because you could also say this guy here, etc., etc. So this d value can change depending on what it is that we see. So we're ready to put it all together now. So let's start writing our sine curve. So using our curve, or our sort of fill in the blank up here. So we have our original sinusoidal function up there. We're going to start off with y. Instead of y, we're going to write h at t, because that's what's on the y-axis. Our a value is 2, so we're just filling it in one by one. So our a value is 2. We're going to write out a sine function, so I'm going to write sine here. Next is our k value. Our k value is 36. And then instead of x, we have t. And we are shifting, for sine, we're shifting to the right 7.5. So it's got to look like minus 7.5. And then don't forget our c value, which is plus 1. And then if we do the same thing for our cosine function, this is what it will look like. So our a value is the same, k value is the same, c value is the same. The only difference is our d value is 0 here. And we have a cos. Okay, so here in this question, we're given that a sinusoidal function has an amplitude of 2 units. Sinusoidal, by the way, isn't a sine function necessarily. It could also be cosine. Has an amplitude of 2 units, a period of 180, and a maximum at the point 0.03. So it says determine an equation of this function and represent it with 2 different functions. So we've got to find our a, our k, our c, and our d. So I think determine the equation of this function, not worded really well, but I think what it's asking is for 2 different equations for this one function. So we're given little pieces of information. We're automatically given our amplitude. We have our period so we can find our k value. The question is, can we find our d value and our c value? So I'm just going to quickly do a sketch of what we know. So I know that there is a maximum point at 0.3. So I know that this is 3. I also know it has an amplitude of 2 units, and that means that the middle of the graph must be here at 1, because the difference from the top to the middle has to be 2, so the middle has to be 1, which means our minimum value has to be 2 below 1, so our amplitude has to be 2, so our minimum value has to be at -1, so I'll just keep that in mind, that I got to bring this all the way down to -1. So I've taken care of this part, our amplitude of 2, our maximum is 0.0, 0 and 3, and we've got to make sure that we have a period of 180. So if I do a graph like this, where it hits a maximum, and I say that this is 180 degrees, then we have our graph, and now all we have to do is come up with an equation. So now that we've had some practice with it, try finding the amplitude and the period in C and D on your own, and then come back to the video to check your answer. So our amplitude is actually already given to us, so we didn't have to do this calculation. We knew the amplitude was supposed to be 2. Our K value can be found by using the relationship with the period, which is 360 over K. And we'll find that the K value is 2. And then our C value, again, is just our equation of the axis of the curve. So this must have been shifted up by 1. And our graph shows our calculation to be true as well. Our D value, again, that's just slightly more tricky. We're just going to do a little, what would we do if it was sine? What would we do if it was cos? It asks us just for 2 different equations, which means we could do two sine functions or 2 cosine functions, but let's just make it easy and do a sine and a cos. So if I were to figure out where cos would start, cos wouldn't have been shifted at all, because the cos is supposed to start at the top of its bowl, and it is right there, and end over here. So that means that the cos curve hasn't been shifted at all. So our D value would be 0. Or maybe you've decided, no, you want your cos curve to start here and it's been shifted over 180, that's fine. In terms of sine, sine does not start down here, don't forget. It starts in the middle at the equation of the axis, and it's going to come up and down. So let me just show you what that would look like. So it would look like this, up and then down again, which means that we can say that our sine curve starts right here. And to figure out where this starts, we just need to do a little bit of math. So remember that everything is symmetrical. So this little guy in the middle here, that's where it reaches its minimum value, it's got to be 90, which means that it's going to reach its middle value in between 90 and 180. And that's going to be at 135. So that means that if you see the sine curve beginning here, it's been shifted over to the right 135. Another option is that you see the sine curve starting here, and that would mean that there's a reflection in the x-axis. Another option again is starting your sine curve to over here and then come up and down. Many options. Choose whichever one you like. So when we put it all together, we have these 2 equations, and yours might be slightly different. Again, just plug it into Desmos and make sure that your equation ends up being the exact same graph that we have pictured above. So this next question says, a group of students are tracking Mr. Bueller riding a Ferris wheel. They know that he reaches a maximum height of 11 meters at 10 seconds and then reaches a minimum height of 1 meter at 55 seconds. At the start of the ride, he was 10 meters off the ground. So it asks us to graph one cycle of the height of Mr. Bueller off the ground in relation to time. So if we were to plot the points first in a t-table, just to confirm, or just to organize ourselves, we know that at the start of the ride he was 10 meters off the ground. So that indicates at a time of 0 he was 10 meters off the ground. And after 10 seconds he reached his maximum height, which was 11. And at 55 seconds he reaches minimum height, which is 1 meter. If we were to plan this really quickly, when would he again reach his maximum height of 11 meters? Well, let's figure out what half of period is. So half of the cycle is going from 10 to 55. So he reaches maximum height at 10 and his minimum height at 55. So it means just thinking about that Ferris wheel that we talked about in the very first lesson. He reaches maximum height at 10, minimum height at 55, which means that there was a total of 45 seconds that it took to get from the top of the wheel to the bottom of the wheel, which means, again, it would take another 45 seconds to move from the bottom of the wheel back to the top of the wheel. So if we add 45 to 55, we will get 100. So that must mean our period is 90. So it must take 90 seconds to get all the way from the top to the bottom back to the top. So I just put a really quick scale together to measure our time versus our height. And so I just went up by 5s on the time and I went up by 1s for the height. Let's quickly graph this. So we know that he starts on the Ferris wheel at 10 meters. So we're going to put a dot here. And after 10 seconds, he's at 11 meters. So after 10 seconds, he's somewhere here. And after 55 seconds, he's at 1 meter. And after 100 seconds, he's back at 11. Okay, so let's connect to these lines, or let's connect these dots. And here's what the graph would look like. So it asks us to graph one cycle. We've actually graphed slightly more than one cycle because the cycle begins here. So the one cycle would be about to here, exactly where it hits 10 meters. So now that we have a picture of it and we have a t-table, can we come up with an equation that models the height of him above the ground? So find your A, your K, your C, your D. Try to find as many as you possibly can and then come back to the video. So let's go over our calculations. So our amplitude, we know, is our max minus our min divided by 2. The maximum height that we could get to on this Ferris wheel was 11 and the minimum height was 1, so our amplitude is 5. Our K value we know we can find from our period. So we figured out that an entire cycle lasted 90 seconds because 45 one way and 45 the other way. So if we take our 90 and put it into our equation, we are going to get a K value of 4. And I'll just confirm our A value. Our A value is 5. In terms of our D value, we know that that's our, oh, you know what, I just realized that I mixed these up. This is not our D value, this is our C value. Okay, so now that's switched. So our C, oh, let's change this guy to D. Okay, so our C value is just going to be whatever the equation of the axis of our curve is, and that's going to be 6 because we add our max and our min together divided by 2. So the middle graph is 6. So our C value is 6, and we're left just with our D value. So let's go back to our graph. So now that we have the graph and our calculations in front of each other, we can just make sure that these numbers make sense. So our amplitude looks like it makes sense that it's 5. The middle of the graph is 6, so the middle of the graph is right over here, and the difference from 11 to 6 is 5, and 6 to 1 is also 5. Our period is 90. As we said, it starts up here, ends here, and it would take 90 seconds to get from this point here to this point here. And finally, our D value. So we have a choice. It said we just have to come up with one equation, meaning that we can either use a sine curve or a cos curve, whatever we prefer. So the easiest is probably seeing a cos curve. So if you see the cos curve here, if we use a cos curve, then we can say this has just been shifted over how much? Well, this point is this point here is 10 and 11. Which means right over here is just 10. So if we see a cos curve, we can say this is a cos curve that's been shifted over to the right 10. If we decide to use sine, we might choose this point here and flip it along the x-axis. So there would be a reflection on the x-axis. That could work too, but I think the easiest here is just use a cos curve because there's that bowl shape right there. So it's shifted over to the right 10. So now that we have that last piece of information, we can put everything into an equation together. So we have our height is going to be equal to our A value, which is 5. We're going to use a cos curve because we saw that the fastest. Our K value is 4. It's been shifted to the right 10 and up 6. And instead of X, I made a little error, we're going to put T because H is a function of T. Our question number C right here, there's a little error. There's not enough room to answer this question. So what we're going to do is we're going to put a star beside it, and we're going to come back to it in class. So for the next questions, I want you to try these on your own. So for each what if statement, indicate how the function you created in B would change. So would it affect our A or K or C or D value, or maybe a combination of them? So try these ones on your own and then come back to the video to check your answer. If you're coming back to check, hopefully you realize that When the wheel spins twice as fast, that means the period will cut in half. So our period would be 45. So what would be changing is our K value. Our K value would change. If the height of the base of the wheel was increased by 5 meters, that means the entire graph would shift up 5 meters. And that indicates a change in our C value. Our C value would increase by 5 meters. Our C value would therefore be 11 meters. And last, what if the diameter of the wheel was increased by 10 meters? So we're not shifting the graph, we're actually stretching the graph. And if we're stretching the graph vertically, that means that there's going to be a change in A. So our maximum value is no longer going to be 11. It's now going to be increased another 10 meters, so it would be 21. And our minimum value would still stay the same, it would be 1 because it hasn't shifted up. So the difference between these two would be 20. So we know that the diameter of the wheel has increased from 10 to 20 meters, so increased by 10 meters. And if our max is 21 and our min is 1, our amplitude is no longer 5, it would double and be 10. We're on to our last question now. So the last question says that we've got this flagpole, and the top of the flagpole is swaying back and forth in high winds. The top sways 10 centimeters to the right and 10 centimeters to the left. So it sort of looks like this. Here's resting position. His resting position would be 0. It's going to swing to the left and to the right and to the left and the right and keep on going. So it asks us to come up with an equation of a sinusoidal function that would model this relationship. So first, always start off with a t-table, and let's fill it in as much as we can. So there's multiple interpretations of this. First of all, it says that at t0, the pole is momentarily at its resting position. So its resting position is at 0. So at time 0, its horizontal distance is 0. So that's what we're measuring, time and horizontal distance. So it doesn't actually say if it goes to the right first or to the left first. So this is open to interpretation. So maybe you interpret it as going to the right first, then the left, then the right, then the left. So if that's how you interpreted it, then we would put our next distance would be 10. After that, it would come back to 0, then go to -10, back to 0, and to 10. So let's just draw that out. So we go back -10, back to 0, back to 10. So let's figure out how much time it will take to get there. So it says the top sways to the left and to the right 300 times every minute. So it goes to the left and to the right 300 times every single minute. So that means there's 300 cycles in 1 minute. So how long would it take just for one cycle? So 300 cycles in 60 seconds. And if I want to know how many seconds in one cycle, I just got to flip this. I want to do 60 seconds per 300 cycles. And if I divide those two, I'm going to get the number of seconds per cycle, and that's going to be 0.2. So we have one cycle that takes place every 0.2 seconds, which means that if we start to fill this in, we can see that one cycle is going to go from 0, 10, 0, -10, and 0. So all the way back like this, that would be one cycle. So one cycle here is from here to here, which means that this entire thing must take 0.2 seconds. So the halfway point would be 0.1, and the half of the halfway point would be 0.05, and that's how we can figure that out. So this must be 0.15. So with this information, just in a t-table, we're able to come up with a bunch of our letters. So we can come up with our amplitude. Our amplitude is going to be our max minus our min divided by 2. So there it is. We can come up with our K value. Our K value is going to be related to our period. And we know that one period is 0.2 seconds. We knew our C value is just our equation of the axis, so the middle of the curve. So it's going to be the max plus the min divided by 2. And in terms of our D, we can just do a very quick sketch. I know the maximum distance that we get to is 10 and our minimum is -10. And at 0, we're at its resting position. So it's going to come up, down, and up and down and up and down like this. So it's going to reach its max, and then its min, and then its max, and its min. And you can see looking at this curve that the easiest curve to approximate this to would be a sine curve, because it already sort of looks like a sine curve. So if we choose a sine curve, it hasn't been shifted over at all. If we choose a cos curve, it's been shifted over 0.05, because this point is 10, 0.05. So let's use a sine curve so that our d value is 0. So whether you chose sine or cos, here are two equations that can work. If you came up with your own, test them in Desmos to make sure that they match up to exactly what we have here.